All right, you may or may not hear my children in the background laughing and stuff, so bear with me. But let's talk about 2.3. So it's all about polynomials. Well, polynomial functions. We talked about polynomials in 2.2, how to add, subtract, multiply, and factor polynomials. So let's talk about polynomial functions a little bit. And I'm calling this section elementary polynomial functions because polynomials are going to be something that we cover in greater detail, I think in chapter 4 of the course. So we're going to do an entire chapter about polynomials. They're really, really interesting. So for now, in this section, the focus is just going to be on what you should already know about polynomials coming into the class. So first of all, if we want to solve a polynomial equation, the way that we do that is we move everything over to one side of the equation, then we factor, and then we apply the zero product principle, which says that if you have two things whose product is 0, then one of the factors has to equal 0, right? In other words, you can't multiply two things together and get 0 unless one of those things is 0, right? If we are dealing with a quadratic, right? So a polynomial, a quadratic is just a polynomial, function that has degree 2, right? So if we come across a quadratic and we can't factor it, then we can always just use the quadratic formula, right? So let's practice. So let's solve this equation. This is a really good example to start off on to show why we solve polynomial equations the way that we do. X squared and x are not like terms, so you can't just combine these two terms, obviously. But you also can't really do much. I mean, you can move the 25x over here and then maybe try to divide through by an x, but then you're going to end up with a negative 84 over x on this side. So there's just no really good way to get rid of the excess x's here. So we deal with them by factoring. That's the strategy. So let's move the 84 over. And then we try to factor. So to factor this, we'd have to think of two numbers that multiply to be 84 and add up to be 25. Can we do it? Oh man, 84 is what? 7 times 12. Is that right? 7 times 12 is 84. 12 plus 7, though, is not 25. Can we get closer? Yeah, I don't know. 84. 84 divided by 4. Oh, 21 and 4. We'll do the trick. 21 and 4. Maybe you thought of that right away and you were like, who is this fool trying to teach me how to factor? Anyway, yeah, 21 and 4. We'll do it. So there you go. So then we get x plus 21 equals 4, or sorry, equals 0, or x plus 4 equals 0. So that would imply that x is negative 21 or x is negative 4. And there you go, right? There's our solution set. So we have those two solutions. Okay? So that's how these things work. And that's always our strategy. Move everything over and then factor. If you can't factor, use the quadratic formula, provided that the equation you're working with is quadratic. So I'm going to let you pause the video and see if you can work out part B on your own. Okay, here's my solution. So I'm going to move everything over and factor. And then apply the zero product property or the zero product principle. maybe from here to here you're wondering, well, where did the x squared go? I mean, of course you can just take the square root, right? If x squared equals 0, then x equals 0. It's got to be 0. Okay, so there's our solution set. 3 solutions this time. If you started with this equation and you started off, well, I'm going to divide through by an x squared, you'll get the -2 and +2 as solutions, but you'll be missing the 0 as a solution. And here's why. It's because division by 0 is not defined, right? So if you take x to the 4th equals 4x squared, and you think, well, I'm just going to divide through by x squared, then you get, x squared equals 4. And then maybe you think, oh, I'll solve that by taking square root. So I get x equals plus or minus 2. And so you get these 2 solutions, but you're missing the x equals 0 because you don't know if x equals 0. If x equals 0, then this step here, dividing through by x squared, is undefined, right? It's not completely illegal to do this. What you have to do is you have to consider the 2 different cases. You have to say case 1, x equals 0, right? And then case 2, x does not equal 0, and then you can do this. But for case 1, that's where you recover the other solution. That's where you recover this 3rd solution of x equals 0. A safer thing to do, though, is to just do what I've said. Move everything over, factor, apply the 0 product principle. Okay, try out part C. I'm going to start working out my solution. Following the same strategy. So I'm not even gonna talk. But if you haven't worked it out, seriously, pause the video, try it out. Okay, here I go. Because I'm running out of space, I'm just going to cut to the chase. One thing that you'll notice is that once you get the factorization, you just change the signs there, and those are your answers, right? So once you get the factorization, I know that the solutions are going to be 5, -2, and +2. Of course, that really only works if you have a 1 as your leading coefficient in each of the factors. If this were like a 3 here, then the answer wouldn't be -21, it would be -7, right? Because you'd have to move over the 21 and then divide by 3. But anyway, that's that. Part D. So this one I'll walk you through just because this is not factorable, right? If you try to think about factoring this, for 3, you only have one choice. It's got to be 3 and 1. Those are the only integers that are going to multiply together to give you 3. But when you add these things up, you don't get a 5x, right? You get a 3x plus an x is a 4x, not a 5x. So this thing is not factorable. So that's when we would resort to the quadratic formula. Now, I'm not going to prove the quadratic formula to you. That's something that you should have seen in a previous algebra class, was a proof of the quadratic formula. If you haven't seen a proof of the quadratic formula, just Google it. If you want to convince yourself, Google proof of the quadratic formula, and all kinds of good videos will come up. Okay, but I'm going to use the quadratic formula here. I'm going to say x equals -b plus or minus square root of b squared minus 4 times a times c over 2a. And then I think that's about as far as it's going to go. One good thing to do is to try to simplify the radical part, which if you don't remember how to do that, we're going to be reviewing it in a few sections from now. So that's one good thing. And then you can also split these if you like. You can call this negative 5/2 plus or minus root 13 over 2. I kind of like doing, I kind of like presenting it this way a little bit better. When you give me your answers, though, make sure to write them as two separate answers. Don't just put the plus or minus sign. Negative 5/2 plus root 13 over 2 is a different solution from negative 5/2 minus root 13 over 2. Okay, and those are the exact values. The other thing that I'll say is don't bother giving me decimals. If I want a decimal approximation, I'll ask for it. I'll say something like, solve this equation, give me a decimal approximation. But most of the time, I don't really care about the decimal approximations. Most of the time, I want the exact answers, and that's what these are. If you give me a decimal approximation and then you round off, I mean, that's not the solution to the equation. That's a number that's close to the solution to the equation, right? But I want the solution, okay? Okay. So that's how we solve polynomial equations. Let's talk about graphing polynomial functions. And at this point in your mathematical career, you're probably only familiar with graphing quadratics. You may be familiar with graphing cubics of a certain form, but probably not even all cubics. So we're going to review both of those, quadratics and cubics. If you've never seen cubics before, don't stress out about it. It's not too difficult. It's very similar to this. But so the standard form of a quadratic function is f of x equals ax squared plus bx plus c. But that's not usually the way that we like the function. That's not usually the format we like the function to be in order to graph it. It's a lot easier to graph it if we write it in this way. F of x equals a times x minus h squared plus k. I'm going to call this the graphing form. Different texts call it different things, but I'm just going to call it the graphing form since that's why we like it. Other books may call it like the vertex form or something else, or they may even call this the standard form and they might call this, I don't know, something else. But for the purposes of this class, we're going to call this the standard form and this the graphing form. So we like graphing functions when they're written in this format because when they're written this way, you can read off exactly what the vertex is. We know that the vertex is the point h, k. So you change the sign of h, do not change the sign of k. That tells you where the vertex of your parabola is, and once you've got the vertex, then you can pretty much figure everything else out. We're going to graph these kinds of functions by graphing transformations of them. So in order to do that, you really need to have a good understanding what f of x equals x squared looks like. So it looks like this, right? We call this a parabola. It's this kind of U, this sort of cross between a U and a V, I guess. And it extends, of course, on and on forever. Anyway, but this point where the graph starts to turn around, that's called the vertex. Some points that are on the graph of f of x equals x squared are these. These are the 5 points that I would like for you to transform when you're graphing a transformation, okay? By the way, you shouldn't have to like memorize this list. This should be fairly obvious, right? Remember that your x coordinate is the input value and the y coordinate is the output value. So if you just think about the function f of x equals x squared, when I input a 0, I'm going to get out a 0. When I input a 1, I'm going to get out a 1. When I input a negative 1, well, negative 1 squared is negative 1 times negative 1. I'm going to get out a positive 1. When I input a 2, I get out a 4. When I input a negative 2, I get out a 4 again. So you don't have to memorize this list of points, but I'm just listing them here so that you know that when I'm grading your test or your quiz or something, I want to see these 5 points, or rather the transformations, their corresponding transformations. So let me give you an example. Let's say that we want to graph this function right here, f of x equals x plus 4 squared minus 2. I'm going to graph this by transforming the original f of x equals x squared kind of parent function, right? I know that the vertex of this function is 0, 0. This is going to shift that vertex 4 units to the left and 2 units down. So instead of the vertex being at 0, 0, it's going to be at 1, 2, 3, 4, 1, 2. It's going to be at -4, -2, right there. I can do that with the other 5 points here, right? Like I could take 1, 1 and go down, or sorry, left 4, 1, 2, 3, 4, down 2, 1, 2, and it ends up right there. But what you notice when you do this is that these points retain the same configuration, right? So in other words, I know that from the vertex, I can sort of think of the vertex as my new origin, if you like. So I can think of this vertex as the point 0, 0. And then these other 4 points are on this graph, right? 1, 1, -1, 1, 2, 4, -2, 4, right? So that's another way to think about graphing transformations. And honestly, that's really the way that I think about it when I'm graphing functions. I don't think about transforming each individual point. I just think about transforming like the vertex. And then once I have the vertex, I know that the configuration of these points is going to stay the same, right? Because they all get shifted the same. Anyway, if I wanted another point on here, I know that the next point on this list would be, 3, 9. Because if I square 3, I get 9. So I could do 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I know that point's on there. It's not totally necessary for you to give me those extra points, but if you want, it doesn't hurt. Okay, so that's what that function looks like. So there's the graph of the function. We're also asked to find the X and Y intercepts. That's not something that you have to do to graph a function, but it's something you should know how to do if you're asked to do it. So let me show you. You find the X and Y intercepts the same way that you find the X and Y intercepts of any function, right? The X-intercepts are the place where the graph crosses the x-axis, right? It's these 2 points right here. And the y-coordinate at those 2 points is going to be 0. So in other words, if I want to find x-intercepts, I just plug in 0 for y. So I'm going to say 0 equals x plus 4 squared minus 2. And then same thing with the y-intercept. If I want to find the y-intercept, the graph is going to cross the y-axis whenever x is 0. So I set x equal to 0. So the y-intercept is f of 0, right? So for the y-intercept, I'll do the y-intercept because it's easier. 16 minus 2 is 14. So the y-intercept is the point 0, 14. The x-intercepts take a little bit more work. We've got to solve this equation for x, right? So I would add the 2 over to the other side. And then I would take the square root. Remember, when you take the square root, you have to have a plus or minus sign. So plus or minus root 2 equals x plus 4. If that's completely foreign to you, don't worry. We'll review it. And then I would move the 4 over. I don't know why I put parentheses around this, but because I just need to subtract 4. So I'm going to get x equals -4 plus or minus square root of 2. So those are the x-intercepts, right? There are 2 of them. -4 plus root 2, comma 0. And then -4 minus root 2, comma 0. Those are the x-intercepts. You could get decimal approximations to see about how much these are, but they should fall approximately here on the graph, right? So that's the idea behind getting x and y intercepts. I'm going to let you try out part B on your own. Okay, so obviously there's a horizontal shift here, but also you're going to have to do some stretching and flipping. Okay, so anyway, pause the video, see if you can work it out on your own. Okay, here's my solution. The vertex is going to be, instead of at 0, 0, it's going to be at -1, 0. And that vertex becomes my new kind of axis system, if you like. All right, so I've got this new axis system where this is my new 0, 0. Now, because of this -2 out here, I'm going to have to flip the graph over, and I'm going to have to stretch the vertical distance between the points by a factor of 2. So whereas on the normal function, I would go over 1 up 1, now I'm going to have to go over 1 down 1 just to take care of the flip. But then I'm also going to have to stretch that vertical distance by 2. So instead of going over 1 down 1, I'm going to go over 1 down 2, right? The vertical distance gets stretched by 2. Same thing in the other direction, over 1 down 2. Okay, and then normally also I would go over 2 up 4. But now I'm going to have to go, just to take care of the negative sign, I would have to go over 2 down 4, 2, 3, 4. But the vertical distance has been stretched by a factor of 2. So actually, instead of going over 4 down 4, I'm going to go, sorry, instead of going over 2 down 4, I'm going to go over 2 down 8, right? So I'm going to double that vertical distance. 1, 2, 3, 4, 5, 6, 7, 8. And then the same thing on the other side, right? It's a mirror image. So that's the graph that I end up with for that function. In this case, finding X and Y intercepts is easy. We've already done it, right? This is the one and only X-intercept, right? So the X-intercept is the point -1, 0. And the Y-intercept is this point right here, that's 0, -2. If you'd like, you could verify that by, to find the X-intercept, you plug in 0 for Y and then solve for X. To find the Y-intercept, plug in 0 for X and then simplify. But these are the points you're going to get. Okay, so that's that one. That's how we take care of these vertical stretches, right? They increase the vertical distance between the points by this factor. Okay. All right. So that's how graphing quadratics works. Let's talk about graphing cubics. So in a similar way, right, we can graph cubic functions of this form, right, a times x minus h cubed plus k, by shifting, by performing transformations. So recall that, well, you may or may not recall this, I don't know, but the cubic function, f of x equals x cubed, it looks like this, right? It looks kind of like a little snake. This function has the points 0, 0, 1, 1, -1, -1, 2, 8, -2, -8 on it. Also, it has other points, of course, but those are the 5 that I'm going to look for when I'm grading your tests and quizzes. I'm going to look to make sure that you transformed those 5 points. But I do this in a very similar way that I did to transforming quadratics, okay? So let me just show you an example and then I'll let you work on part B on your own. But here we've got x minus 2 cubed plus 1. This tells me that I'm going to shift right 2 and up 1. So instead of having I call this the center point. It's not the vertex, but it's that point right there. It's an inflection point. So, but instead of that inflection point being at 0, 0, now it's going to be at 2, 1. Right? I go right 2, up 1. And that's my new, I can think of that like my new origin. Okay? So all I'm going to do now is graph the normal cubic function, but with respect to this new kind of coordinate system, right? So 0, 0, this is my new 0, 0. Then I have 1, 1. And I have 2, 8. 2, 3, 4, 5, 6, 7, 8. And I have -1, -1. -2, -8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then connect the dot with a cubic looking curve, and you're done. That was kind of ugly, but you get the idea. Okay, so that's that. I'll let you go ahead and pause the video, see if you can do part B on your own. Okay, here's my solution. First of all, I noticed that I'm going to be shifting the graph down 1. So instead of the vertex being at 0, 0, it's going to be at 0, -1. And then the next thing that I notice is that it's been flipped over, right? It's been flipped over. So again, I'm thinking of this as my new coordinate system. Instead of the graph kind of flowing this way, it's going to flow this way, right? Because it's got to be flipped over. So, so instead of going to 1, 1, I'm actually going to go to 1, negative 1. Instead of 2, 8, I'm going to go to 2, negative 8. 1, 2, 3, 4, 5, 6, 7, 8. Same thing in the other direction, right? Instead of negative 1, I'm going to go negative 1, positive 1. And negative 2, positive 8. 1, 2, 3, 4, 5, 6, 7, 8. And that's what that one looks like. Okay, so graphing these things hopefully is not too terrible for you. Now, these graphs that we've done so far have been given to us in this nice graphing form, right? This nice graphing form up here. That's not always how these things are given to us, right? So we want to be able to graph quadratic and cubic equations that are not written in graphing forms. This is not easy to do with cubic functions, actually. And so we're going to come back to that topic in, I think, chapter 4. However, we can graph quadratic functions that are written in standard form. And the way that I like to do it is I like to find the vertex first. There are a couple ways you could do this. One way you could do it is by completing the square, right? So you could complete the square on this so that it's been rewritten in graphing form. But to me, that just takes a lot more work than just finding the vertex using this vertex formula. So let me just show you how to use the vertex formula. I think this is a really nasty graph. But let me just show you. This is sort of a worst case scenario. This is as bad as it's going to get. So let's graph this thing and let's use the vertex formula. It says find the vertex, then find the intercepts and graph the function. So let's do that. So as far as the vertex is concerned, x equals negative b over 2a, right? B is the coefficient on the x term, a is the coefficient on the x squared term. So x is going to be negative b over 2a. Okay. Well, the 3's will cancel. At least the negative signs will cancel. This is going to be 1/2, right? So x equals 1/2. And then to get the y coordinate of the vertex, we plug 1/2 into the function, right? So maybe I should say y equals f of 1/2. So that's 3 times 1/2 squared minus 3 times 1/2 minus 6. You can use your calculator if you want. 1/2 squared is 1/4. 3 times 1/4 is 3/4. 3/4 minus 3/2 minus 6. 3/2 is the same thing as 6/4. And 6 is the same thing as 24/4. I'm just getting common denominators, right? But I've got 3/4 minus 6/4. That's negative 3/4. And then minus 24/4. Actually, maybe I'll do it like this. I've got negative 3/4 minus 6. So I think that should be negative 6 3/4, right? That's even easier. That'll be easier to graph. Okay, so the vertex is the point 1/2, negative 6 3/4. By the way, it might be good at this point to stop and just say, if you didn't like my mental math here, you're not required to use it. Any way that you arrive at this answer is fine with me. So don't get too caught up on those details, right? You don't have to memorize like step by step. Oh, how did you do this? Okay, so now you do this. Now you get a common denominator. Now you do this. It's like, no, just do the arithmetic, right? Do the arithmetic however you like to do it, right? But you've got to end up at this point. Okay, so there's the vertex. Once you have the vertex, right? So I'm going to plot this thing 1/2 and then -6 3/4. 1, 2, 3, 4, 5, 6 3/4. So you're somewhere here in no man's land, right? 1/2 and -6 3/4. But that vertex becomes the origin of your new coordinate system. And then the other points on the parabola, they retain the same configuration that they always do. So you know that, well, except that you're multiplying by a factor of 3, right? So the vertical distance between the points is going to be scaled by a factor of 3. But you know that if you go over 1, on the parent function, you would go up 1. Now, since this has been scaled by a factor of 3, you're going to go up 3, right? So over 1, up 3, 1, 2, 3. Same way in the other direction, over 1, up 3, 1, 2, 3. If you go over 2, you're going to go up 4, usually, except that this has been scaled by a factor of 3, so you're actually going to go up 4 times 3 is 12, right? So if I go over 2, you're going to go up 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm going to have a mirror image of it on the other side as well. And that's good enough, right? So you've got your 5 points. You could connect the dots, and you've got a graph of the function. Now we were asked explicitly to find the intercepts as well, though. So I'm going to do that now. Let's find the X-Intercepts. To find the X-Intercepts, we plug in 0 for y, and we would say 0 equals 3x squared minus 3x minus 6. Oh, what a nasty one. Well, we can factor out a 3 at least. And I'm going to just divide through by 3, you know. I'm going to get 0 equals x squared minus x minus 2. Can we factor? Oh, I think we can factor that, yeah. We can get x minus 2 times x plus 1. That gives us our x-intercepts, right? So our x-intercepts are the points 2, 0, and -1, 0. Let's see if that corresponds to what we kind of would have expected to happen. So 2, 0, 1, 2. These points are with respect to the original axis system, of course, right? So 2, 0 there, and -1, 0 there. Yeah, that's still looking pretty good, right? Still looking pretty good. Finally, our y-intercept. We get that by plugging in 0 for x. So f of 0 is 3 times 0 squared minus 3 times 0 minus 6. That's just -6, right? So 0, -6 is the y-intercept. 0, 1, 2, 3, 4, 5, 6. There's the y-intercept right there. It makes sense. So we can connect the dots. Okay, and that's what that function looks like. Okay, so we can graph these kinds of functions as well. Again, the cubic case, though, is a lot more complicated, and so it's something that we'll come back to in a later chapter. Okay, I want to finish off by giving you a couple of applications of quadratic functions in particular. One thing that we notice by looking at the graph of a quadratic function is that if the graph opens up, right? So if the graph opens this way, then we're going to have a minimum value, right? If the graph opens down, then we're going to have a maximum value. And those minima and maxima, they always occur at the vertex of the parabola. So if you have a question that says something like find the maximum or minimum of the function, well, first of all, you know that you're going to have a maximum if the graph opens down and a minimum if the graph opens up. But then second of all, to find that maximum or minimum is the same thing as just finding the vertex of the parabola. So let's practice doing that. So on part A, I think I said already, you're going to have a maximum because this thing opens down, right? Right, so you've got a maximum. I don't know if that's accurate at all. I don't know if that's what the function looks like, but I do know that the function opens down, so you've got to have a maximum. Where does the maximum occur? Well, it occurs at the vertex. What's the vertex of this parabola? Well, this is given to us in graphing form, so it's really easy to tell what the vertex of the parabola is. It's the point -7, 1. Right? So there's almost no work to be done here. The maximum is the point -7, 1. And that's all there is to it. Right? No minimum. Right? There's no minimum here. Right? This keeps getting smaller and smaller and smaller the further you go. So there's no minimum value. But there is a maximum value at -7, 1. Part B, on the other hand, is going to have a minimum value but no maximum because it opens up, right? It's going to have a minimum but no maximum. Okay. Now here we're not given the function in graphing form. So this is where you would use the vertex formula. You would say, all right, I just need to find the vertex. So I'm going to use the formula x equals -b over 2a. That's going to be 3/4. That's the x-coordinate of my vertex. Now to find the y-coordinate of my vertex, the y-coordinate is going to be f of 3/4. Right? I have a feeling this is going to get a little nasty. 4ths plus 3. So let's see. This is going to be 2 times 9/16 minus 9/4 plus 3. I can cross cancel the 2 here. Then we're going to have 9/8 minus 9/4 plus 3. And then you've got to add those things up, however you like to do it, right? I'm going to think 9/4 is 18/8. 9/8 minus 18/8 is -9/8. So these first two things are going to combine to give me a -9/8. Now here I've got a positive 3. So I've got to do a 3 minus a 9/8. 9/8 is 1 1/8, right? So 3 minus 1 1/8 is going to be like a little less than 2. It's going to be like 1 7/8, right? So this is going to be 1 7/8. Again, if you don't like that, do it a different way. But the vertex, I think you should end up with is 3/4 and then 1 7/8. So this is the minimum. Okay. Now, why are we interested in maxima minima? Well, because of things like projectile motion, which we've already seen some applications, or we've already seen some examples of projectile motion in this class. Projectile motion, anything that you want to maximize or minimize, profits, right? So if you want to maximize the profit that a company makes or whatever, I mean anything, right? Anything that where a maximum or minimum is, like anytime you want to maximize or minimize something, right? This concept could come in handy. So, for example, it says a ball is thrown straight up in the air with an initial velocity of 56 feet per second from a platform 50 feet above ground. As we discussed in section 1.9, we know that the height of the projectile after t seconds is going to be -16t squared plus 56t plus 50. Part A asks us, what is the maximum height the projectile reaches? Well, this is quadratic. Its graph is a parabola, and that parabola opens down because of the negative sign out in front, which means you've got a maximum, and that maximum happens at the vertex of the parabola. So this is just a fancy way of asking, what's the vertex of this parabola? So let's find it. So the vertex x equals -b over 2a. The negatives will cancel at least. Let's see, I'm going to use my calculator. 56 divided by 32 is 7/4. It reduces to 7/4. Okay? The y coordinate now is going to be p of 7/4. So p of 7/4 is negative 16 times 7/4 plus 56 times 7/4 plus 50. I'm just going to punch this into my calculator to see what I get. Oh, so you should get exactly 120. That's pretty nice. Okay, now the interpretation of this is important, right? Here I call it x, I really should have called it t, right? T is the amount of time that passes. P of t is the height of the projectile. So if you want to answer the question, what's the maximum height? The answer is 120 feet, right? That's the maximum height. The 7/4 is how long it takes for the projectile to reach that height, right? So it takes 7/4, so 1 3/4 second, 1.75 seconds for the projectile to reach its maximum height of 120 feet. So the maximum height itself is the 120 feet. It takes 1 3/4 of a second for it to reach that height. Okay. Part B says, what is the velocity function for the projectile? Ooh, okay, so this is asking us to calculate a derivative, right? Remember, the velocity function is the derivative of the position function. So let's remind ourselves, right? The position function was negative 16t squared plus 56t plus 50, I believe. Yes. So we need to find the derivative of that. So the velocity function is the derivative of the position function. That's going to be the limit as h approaches 0 of p of t plus h minus p of t divided by h. Okay, p of t plus h, that's going to be negative 16 times t plus h squared plus 56 times t plus h plus 50. All right, that's just the p of t plus h part. Then we have to subtract off p of t. P of t is negative 16t squared plus 56t plus 50. So we have p of t plus h minus p of t. Now we have to divide by h. And now our goal really is to get rid of this h in the denominator so that we can plug in 0. If we plug in 0 now, it's going to be undefined, right? So let's see what simplifying we can do. T plus h squared is going to be t squared plus 2ht plus h squared, right? So I'm going to have negative 16 times t squared plus 2ht plus h squared. I'm going to go ahead and distribute the 56. I'm going to go ahead and distribute that negative sign, so I have a positive 16t squared, a negative 56t, and a negative 50. And let's distribute the negative 16. Whoops. Minus 32ht minus 16h squared. And then a bunch of things should cancel. I think that cancels that. Sorry, this cancels that. This cancels that. And the three terms that we have left over all have an h in them. So we can factor it out and then cancel with the h in the denominator. Okay, and now at this point we can safely plug in 0 for h. And that term's just going to cancel, right? So we're going to get negative 32t plus 56. There's our velocity function. Maybe I'll say this equals v of t. Right? So there's our velocity. There's our velocity function. Okay. So then part C says, what is the height of the projectile at t equals 1 second? How fast is the projectile moving at that time? Well, the height of the projectile is going to be p of 1. That's negative 16 plus 56 plus 50, which I think equals 90. Right, so it's 90 feet above ground after 1 second. How fast is it moving at that time? So how fast is it moving? Let's see. That's going to be negative 32 times 1 plus 56. What's 56 minus 32? 24? 24 feet per second. Okay, it started off at 56 feet per second. After 1 second, it's already slowed down to 24 feet per second because gravity's immediately starting to try to pull it back down to Earth, right? Okay, part D, how fast is the projectile moving when it hits the ground? Oh, okay, how fast is it moving when it hits the ground? Let's see. In order to answer that question, we first of all need to figure out how long it takes to hit the ground. And so for that, we're going to use the position function. We're going to say, when the projectile hits the ground, its position is 0, right? It's 0 feet from the ground at that point in time. So we're going to plug in 0 for the position and then solve for t so that we know how long it takes. Once we know how long it takes, then we can plug in that value for t into the velocity function to figure out how fast it's moving. Okay, so step 1, find how long it takes to hit the ground. Step 2, plug that into the velocity function. So let's do it. So I'm going to plug in 0 for the position function and then solve for t. Oh, this is kind of nasty, isn't it? I think the best we can do would be to maybe factor out a 2. So if I divide through by 2, I'm going to get 0 equals negative 8t squared plus, oh, what is 56 divided by 2? 28. And 50 divided by 2 is 25. Oh, man. So then to try to factor that. Well, for 25, I don't have too many options, right? 5 and 5 or 25 and 1. For 8, I have a couple options, 8 and 1 or 4 and 2. Maybe I should divide through by a negative as well. That'll make things a little easier at least. At least for me. Oh, 25. Okay, well, let's try. Maybe it's not even factorable. I don't think this is going to work out, right? We get 40 minus 5. That's 35, not 28. Not 28 we're looking for. So I don't think that's going to work for us. If I put a 1 here and a 25 there, we'd get 25 and then 8. That's not going to give us 28 though. So I don't think 25 and 1 would work either. Let's try 4 and 2. Here I would get 20 minus 10. So that's not going to do it. I don't know. I kind of suspect that this thing doesn't factor. I could try with 25 and 1. Oh, that gets me kind of, no, that gets me further away. Because then I would have 50. I could try 25 there, that's even worse. So yeah, I kind of suspect this thing doesn't factor. We'd have to use quadratic then. So I'm going to say t equals negative b plus or minus the square root of b squared. Oh, what's 28 squared? 784. Minus 4 times a times c over 2a. Oh yeah, that's gotta be nasty. 28 plus or minus square root do 784 plus 4 times 8 times 25. It's 1584 over 16. Is that a perfect square? Square root of 1584? No, it's not. Yeah, so yeah, this thing would not have been factorable. Shh. Okay, so 28 plus square root 1584 divided by 16 is approximately 4.2. That's if we add. Now if we subtract, then we get negative 0.7. So one of these answers makes sense and the other one doesn't, right? This one doesn't make sense because it means that the thing hit the ground 0.7 seconds before we launched it, right? The reason for that is because we started at a platform 50 feet above ground, right? So the function, right? The function looks kind of like this. If we imagine the x-axis is the ground, function is looking something like that. And so it's saying, well, you know, if you're starting 50 feet above ground, it's going to go up for a while, and then it's going to come back down. This is the 4.2 seconds, right? This is the negative 0.7 seconds. So I think 4.2 seconds is the time that we want to plug in. So that we're going to say, all right, that's how long it takes for the projectile to hit the ground. Now, how fast is it going, right? So we're going to say, what's v of 4.2? V of 4.2 is going to be negative 32 times 4.2 plus 56. And let's see. That comes out to negative 78.4 feet per second. So that's how fast the projectile is moving when it hits the ground. Negative because it's moving down, right? It's moving down toward the ground. So that was quite a hefty problem. Oh, and that does it for this section. So thanks for hanging in there, and we'll see you in the next one.